Hold out your hand in front of you. Look at it. The distance from the tip of your middle finger to your wrist, approximately 18 centimeters for an average adult hand, is a scale that your nervous system understands directly. You can feel 18 centimeters. You have a physical intuition for what it means. Now consider that if you scaled the sun down to the size of that hand, 18 centimeters from fingertip to wrist, the largest star ever discovered would be approximately 230 meters tall, the height of a 70-story skyscraper. You are holding the sun in your palm, and the largest known star towers above you like a building. The star is called UY Scuti. It sits approximately 9,500 light-years from Earth in the constellation Scutum, the Shield, a small constellation near the center of the Milky Way. It is a red hypergiant, the most extreme classification in the stellar taxonomy, a category reserved for stars that have pushed beyond even the ordinary boundaries of stellar excess into a regime of size and luminosity that challenges every intuition we have about what a star can be. UY Scuti has a radius of approximately 1,708 times the radius of the Sun. This number requires some unpacking, because it is large enough to be functionally meaningless on first encounter. The Sun's radius is approximately 696,000 kilometers. Multiply that by 1,708 and you get approximately 1.19 billion kilometers, a sphere with a radius of 1.19 billion kilometers. If UY Scuti were placed at the center of our solar system, where the Sun currently sits, its surface would extend beyond the orbit of Jupiter. Not to Jupiter, beyond Jupiter, past the fifth planet from the Sun, into the space where the asteroid belt gives way to the outer solar system. Jupiter is approximately 778 million kilometers from the Sun. UY Scuti's surface, centered on our Sun's position, would extend to approximately 1.19 billion kilometers, engulfing Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter, and reaching approximately 400 million kilometers past Jupiter's current orbit. The Earth would be deep inside the star, not on its surface, inside it. Approximately 148 million kilometers beneath the photosphere of a star whose surface temperature is roughly 3,400 Kelvin, about 60% of the Sun's surface temperature, but distributed over a sphere so vast that the total luminosity is approximately 340,000 times the Sun's. A star that cool should not be that luminous. The luminosity comes entirely from the size. UY Scuti shines with the power of 340,000 suns, not because it burns hotter, but because it burns across an area so immense that the combined output of every square kilometer of its surface adds up to something that dwarfs everything else in its neighborhood of the galaxy. Tonight, we are going to examine what UY Scuti actually is, how it formed, what is happening inside it, what its surface and atmosphere are like, what will happen to it, and what its existence tells us about the extreme upper limits of stellar physics. Not the comfortable summary, the detailed picture, the one that includes the genuine uncertainties, the real scientific debates, and the strange and counterintuitive properties of a star so large that the ordinary concepts we use to describe stellar physics apply to it only in modified and sometimes paradoxical forms. Before we begin, if you are here because the night is long and you need something substantial to settle into, stay with this. What follows is worth the time. Let us start with the question of measurement, because the specific claim that UY Scuti is the largest known star, with a radius of 1,708 solar radii, is not as straightforward as it sounds, and understanding its complexity is essential for understanding what the star actually is. Measuring the radius of a star is not a matter of holding up a ruler. Stars are point sources of light at the distances we observe them. Even the nearest stars beyond the Sun appear as pinpoints in all but the very largest telescopes under the very best conditions. Measuring stellar radii requires indirect methods that combine measurements of different physical quantities. The most direct method for nearby large stars uses a technique called interferometry, combining light from multiple telescopes separated by large distances to achieve angular resolution far beyond what any single telescope can provide. The angular diameter of a star, the angle it subtends in the sky as seen from Earth, combined with its known distance gives the physical diameter. For UY Scuti, the angular diameter is approximately 5.48 milliarcseconds, an angle so small that fitting 65 million UY Scutis side by side across the sky would be needed to span the full moon's diameter. Measuring an angle this small requires interferometry, with baselines of hundreds of meters or more. The Very Large Telescope Interferometer at the European Southern Observatory in Chile has measured UY Scuti's angular diameter directly using exactly this technique. The measurement combines the output of multiple 8.2 meter telescopes using interferometric combination of their light to achieve angular resolution equivalent to a telescope approximately 130 meters in diameter. The measurement of angular diameter gives the physical radius only if the distance to the star is known. Distance measurement for stars as far as UY Scuti, approximately 9,500 light-years, is itself uncertain and is the primary source of uncertainty in the radius estimate. Distance measurements at this range use the technique of spectroscopic parallax, comparing the observed brightness and spectrum of the star to calibrated models of stellar luminosity as a function of spectral type, combined with other indicators. The uncertainty in the distance to UY Scuti translates directly into uncertainty in its physical radius. The most careful analysis of the available data gives a radius of approximately 1,708 solar radii, with an uncertainty of approximately 192 solar radii, meaning the true radius could be anywhere from approximately 1,516 to 1,900 solar radii. This uncertainty is large in absolute terms, a range of 384 solar radii, but the central value is clearly in the range that makes UY Scuti the largest star known, and even the lower bound of the uncertainty range would keep it among the largest known stars. There is also a specific complication with UY Scuti that affects the radius measurement. The star is surrounded by an extended atmosphere and envelope of gas that has been shed from its surface, a circumstellar envelope of expelled material that extends far beyond the photosphere. The boundary between the photosphere and the extended envelope is not sharp. Different observational techniques that are sensitive to different layers of the atmosphere give somewhat different radius estimates depending on which layer they are tracing. The interferometric measurement traces approximately the photosphere, but there is genuine uncertainty about where exactly the photospheric boundary lies in a star that is actively losing mass at an extraordinary rate. What is not in dispute is that UY Scuti is genuinely enormous, genuinely in the category of the largest stars known, and genuinely far larger than anything in the ordinary experience of stellar astronomy. The specific number, 1708 solar radii, is the best current estimate with appropriate uncertainty. The claim that it is the largest known star is supported by the available data, while acknowledging that other candidates exist and that measurements of all very large stars carry significant uncertainties. Let us now talk about the specific category that UY Scuti belongs to, the red hypergiants, and why this category represents one of the most extreme phases of stellar evolution, accessible only to stars that started with masses many times the Sun's mass. Stellar classification is a system based primarily on the surface temperature of a star, which determines its color and spectral characteristics. The main spectral classes, from hottest to coolest, are O, B, A, F, G, K, M, with each class further subdivided numerically from 0 to 9. The Sun is a G2 star with a surface temperature of approximately 5,778 Kelvin. UY Scuti is an M2 star with a surface temperature of approximately 3,400 Kelvin. Cool for a star, which is why it appears red rather than yellow-white like the Sun. The luminosity classification provides a second dimension, a Roman numeral suffix that indicates the star's position in the Hertzsprung-Russell diagram, which plots stellar luminosity against surface temperature. Class 5 stars are main sequence stars burning hydrogen in their cores. Class 3 stars are giants that have evolved off the main sequence. Class 1 stars are supergiants. Class 0 stars, sometimes written IA+, are the most luminous supergiants, the hypergiants. UY Scuti is classified M2IA+, the most extreme luminosity category. The hypergiant classification is reserved for stars with luminosities exceeding approximately 500,000 solar luminosities. Stars that are burning their fuel at rates so extreme that their lifetimes are measured in millions of years, rather than the billions of years available to stars like the Sun. UY Scuti, at approximately 340,000 solar luminosities, sits at the lower end of the hypergiant luminosity range, but its physical size is among the largest of any hypergiant, a consequence of its very cool surface temperature combined with its large luminosity. The Hertzsprung-Russell diagram, the foundational tool of stellar astrophysics that maps the relationship between stellar luminosity and surface temperature, has an upper boundary. It is called the Humphreys-Davidson limit, after the astronomers Roberta Humphreys and Chris Davidson, who characterized it in 1979. Stars above a certain luminosity simply do not exist in stable form with certain combinations of luminosity and surface temperature. The region above the Humphreys-Davidson limit is unstable. Stars that move into it shed mass violently, driving themselves back below the limit or evolving rapidly in ways that prevent stable occupation of the forbidden zone. UY Scuti approaches the Humphreys-Davidson limit. Its position near this boundary tells us something important. It is a star in an extreme and unstable phase of evolution, shedding mass at rates that cannot be sustained indefinitely, evolving on astronomical timescales, but rapidly by stellar standards. Understanding why a star gets to this phase requires understanding the late stages of massive star evolution. Let us trace UY Scuti's history from its formation. A star that ends up as a red hypergiant must have started life with a mass of approximately 25 to 40 solar masses or more. UY Scuti's current mass is estimated at approximately 7 to 10 solar masses. It has already shed the majority of its initial mass through stellar winds and outbursts over its lifetime. The initial mass was likely significantly larger, perhaps 25 to 40 solar masses, in the range where the eventual evolutionary fate is to become a red supergiant or hypergiant before dying in a supernova. A star of 25 to 40 solar masses forms from the gravitational collapse of a dense molecular cloud. The collapse is rapid by stellar standards, a few million years from the initial cloud collapse to an ignited main sequence star. The star arrives on the main sequence, the region of the Hertzsprung-Russell diagram where stars burning hydrogen in their cores reside, with a luminosity perhaps 200,000 to 1 million times the Sun's, and a surface temperature perhaps 35,000 to 45,000 Kelvin. It is a blue supergiant, or O-type supergiant, brilliant, hot, and voraciously consuming its hydrogen fuel. The main sequence lifetime of such a massive star is approximately 3 to 8 million years, compared to the Sun's expected 10 billion year main sequence lifetime. The more massive a star, the shorter its main sequence lifetime, because the core temperature and pressure are higher, driving faster nuclear reactions, consuming the fuel more quickly. A star that is 25 times the Sun's mass burns its fuel approximately 25 to the power of 3 times faster, roughly 15,000 times faster, but has only 25 times more fuel to burn. It lives for approximately 15,000 divided by 25, roughly 600 times shorter than the Sun. A rough calculation that gives approximately 17 million years compared to the Sun's 10 billion, consistent with the more precise estimates. When the hydrogen in the core is exhausted, the core contracts and heats, while the outer envelope expands and cools. The star moves off the main sequence to the right on the Hertzsprung-Russell diagram, toward cooler surface temperatures and larger radii. It becomes first a yellow supergiant, then a red supergiant, potentially oscillating back and forth across the diagram depending on the specific mass and composition. The expansion of the envelope is dramatic, the radius increasing from tens to hundreds to potentially thousands of solar radii. For UY Scuti's progenitor, the star it was before mass loss reduced it to its current 7 to 10 solar masses, the evolution to a red hypergiant represents the late stages of this post-main sequence expansion. The helium in the core is being burned to carbon and oxygen through the triple alpha process. Shell burning of hydrogen continues outside the core. The structure of the star is complex. Nested shells of different nuclei burning at different temperatures, each contributing to the star's luminosity and to the pressure support that keeps the outer envelope from collapsing. What is happening inside UY Scuti right now is an extraordinarily complex nuclear and physical system. The core, a region perhaps only a few thousand kilometers in radius, tiny compared to the star's billion-kilometer total radius, is burning helium at temperatures of approximately 200 million Kelvin. Outside the helium-burning core is a shell of hydrogen still burning at lower temperatures. Outside that is the vast convective envelope, the region through which energy is transported not by radiation, but by the physical movement of huge convective cells. The convective cells in red supergiants and hypergiants are themselves objects of extraordinary scale. In the Sun convective cells, the granules visible in high-resolution solar images are approximately 1,000 kilometers in diameter. In a star the size of UY Scuti, the convective cells are correspondingly larger, potentially hundreds of millions of kilometers in diameter. A single convective cell in UY Scuti might be larger than the entire Sun. These cells carry hot material upward from deeper layers, dump their heat at the photosphere, cool, and sink back down in a churning, turbulent circulation that operates on timescales of years to decades, dramatically different from the minutes-long timescale of solar convective cells. This convective turbulence has observable consequences. The photosphere of UY Scuti is not a smooth, uniform surface. It is a roiling, irregular, variable surface, with regions hotter and brighter than average, and regions cooler and dimmer than average. The star pulsates, its radius and luminosity varying on timescales of years, because the convective cells and the pulsational modes of the stellar structure interact in complex ways. The period of UY Scuti's main pulsational variation is approximately 740 days, just over 2 years, with an amplitude in the visible light of approximately 1 magnitude, meaning the star becomes approximately 2.5 times brighter at maximum than at minimum over this 2-year cycle. These pulsations are not a small perturbation on an otherwise stable structure. They are fundamental to the physical character of a red hypergiant. The outer envelope is loosely bound. The gravitational force per unit mass at the photosphere is much lower than in more compact stars because the density of the envelope is very low and the surface gravity is correspondingly weak. The ratio of radiation pressure to gas pressure is large. The enormous luminosity of the star pushes outward against gravity with a force that approaches the gravitational force in magnitude. The outer layers of the star are in a constant battle between gravity pulling inward and radiation pressure and convective turbulence pushing outward. This balance, or near imbalance, drives the extraordinary mass loss rate of UY Scuti. The star is shedding approximately 58 to 200 times 10 to the negative 6 solar masses per year. That is between 58 millionths and 200 millionths of the Sun's mass evaporating from its surface every year. To put this in perspective, the Sun loses approximately 10 to the negative 14 solar masses per year through the solar wind. UY Scuti loses between 5 million and 20 million times more mass per year than the Sun. At this rate of mass loss, UY Scuti will shed a significant fraction of its remaining mass over the next few 100,000 years. The mass loss is not uniform. It varies with the pulsational cycle and with occasional dramatic outbursts in which the star expels large amounts of material in episodic events that contribute to the extended circumstellar envelope visible around the star. This circumstellar envelope, a shell of gas and dust extending far beyond the photosphere, is one of the reasons measuring the true photospheric radius of UY Scuti is challenging. The envelope contributes to the star's observable appearance in ways that can be confused with the photosphere itself at some wavelengths. Let us talk about what you would experience if you could somehow be placed near UY Scuti, not in a fantasy sense, but as a precise physical description of the environment near the most gigantic star known. At a distance of 1 astronomical unit from UY Scuti, the distance of Earth from the Sun, you would be approximately 148 million kilometers from the center of UY Scuti. But UY Scuti's photosphere extends to approximately 1.19 billion kilometers from its center. So standing 1 astronomical unit from the center of UY Scuti, you would be approximately 1 billion kilometers inside the star. You are not near UY Scuti at that distance. You are inside it, deep inside it. To be near the surface, At a distance comparable to being in the vicinity of UY Scuti's photosphere, you would need to be at a distance of approximately 1.2 billion kilometers from the center. At that distance, you would be in the immediate vicinity of the photosphere, a region of gas at approximately 3,400 Kelvin, with a density similar to a laboratory vacuum by Earth standards, but dense enough to be opaque on the scale of the stellar radius. The sky from that position would be overwhelmingly dominated by the star itself. A star that fills a large fraction of your entire sky, glowing a deep red-orange. Not the brilliant yellow-white of the Sun, but a cooler, dimmer, reddish glow that nonetheless carries 340,000 times the Sun's total power. The radiation environment would be intensely hostile, not as hot as being near a hotter star, but the sheer luminosity would irradiate anything nearby with energy levels far beyond what any known biological or mechanical system could survive. The circumstellar envelope, the gas and dust expelled from the stellar surface, would be visible as a haze surrounding the photosphere. This material is moving outward from the star at velocities of perhaps 20 to 40 kilometers per second, driven by radiation pressure on the dust grains in the envelope, which then drag the gas along through momentum transfer. The envelope extends to distances of many stellar radii from the surface and would appear as a nebula surrounding the star, dense enough near the surface to obscure the photosphere at some wavelengths, thinning with distance as it expands into interstellar space. The space around UY Scuti is being actively enriched with material shed from the star. Oxygen, carbon, nitrogen, neon, and other elements processed in the stellar interior and brought to the surface by convective mixing, then expelled into the surrounding interstellar medium. This chemical enrichment of the interstellar medium by evolved massive stars is one of the primary mechanisms by which the elements necessary for planetary formation and for life are distributed through the galaxy. The material being expelled from UY Scuti today will, in millions of years, become part of the molecular clouds from which future stars and planetary systems form. The atoms leaving UY Scuti's surface right now will eventually, over timescales of millions to hundreds of millions of years, find their way into new stars, new planets, and potentially into the chemistry of life on worlds not yet formed. This connection between the largest star known and the origin of the atoms that make up the smallest and most complex objects known, living organisms, is not metaphorical. It is the literal, physical mechanism by which the universe builds complexity from simpler starting materials. Stars are the universe's nucleosynthesis engines. Massive stars like UY Scuti are the most prolific of these engines, not because they produce the most total material, they are relatively rare, but because they produce the specific mix of heavy elements and spread them most violently into the interstellar medium through their powerful winds and eventual supernova explosions. Think about that for a moment. The oxygen in your blood, the oxygen your heart is right now pumping through your body as you read this, was forged in the core of a massive star that died before the sun existed. The carbon in your DNA was synthesized in a stellar interior at temperatures of hundreds of millions of degrees. The iron in your hemoglobin was produced in the final seconds of a supernova explosion somewhere in this galaxy billions of years ago. You are not made of star stuff in a poetic, metaphorical sense. You are made of star stuff in the most literal, chemically precise sense that physics allows. And stars like UY Scuti are the factories that made the raw materials. But UY Scuti is not just a factory running at steady state. It is a factory in the process of coming apart. And the way it comes apart, the specific sequence of physical events that will end its existence as a recognizable stellar object, is one of the most violent processes in the observable universe, operating on timescales short enough to matter on astronomical scales, and releasing energies that make every other event in the solar system's history look negligible by comparison. To understand what is coming for UY Scuti, you have to understand what is happening in its core right now, and more specifically, what is not happening that will eventually trigger the end. The core of UY Scuti is currently burning helium, fusing helium nuclei into carbon and oxygen through the triple alpha process. 3 helium nuclei, each with 2 protons and 2 neutrons, fuse in a 2-step reaction to produce a carbon nucleus with 6 protons and 6 neutrons. Some of those carbon nuclei capture additional helium nuclei to produce oxygen. The triple alpha process requires temperatures of approximately 100 to 200 million Kelvin, temperatures that exist only in the dense, compressed cores of evolved massive stars. The energy released by helium burning is less per unit mass than the energy released by hydrogen burning. Hydrogen fusion converts approximately 0.7% of the fused mass into energy. Helium fusion converts approximately 0.06% of the fused mass into energy, roughly 10 times less efficient. This means the helium-burning phase of a massive star's life is both shorter and more urgent than the hydrogen-burning phase. The star must burn its helium faster to maintain the pressure support that keeps the core from collapsing. But burning faster depletes the fuel more quickly, which makes the phase shorter still. For a star of UY Scuti's original mass, the helium-burning phase lasts approximately 500,000 to 1 million years, already dramatically shorter than the main sequence hydrogen-burning phase of several million years. After the helium is exhausted, the core contracts and heats further, reaching temperatures sufficient to burn carbon, approximately 600 million Kelvin. Carbon burning lasts perhaps a few hundred years. Neon burning, oxygen burning, silicon burning follow in rapid succession, each phase shorter than the last, each requiring higher temperatures and producing less energy per unit mass. Silicon burning, the final stage before the end, lasts approximately 1 day. 1 day after millions of years of stellar evolution to burn through the silicon in the core and produce iron. And iron is where everything stops. Iron is the endpoint of stellar nucleosynthesis in the specific sense that iron has the highest binding energy per nucleon of any element. Fusing iron nuclei into heavier elements requires energy rather than releasing it. A stellar core that has accumulated iron has nothing left to burn. There is no nuclear reaction it can initiate that will release energy to support itself against gravity. The core that has sustained itself for millions of years through the energy of nuclear fusion suddenly has no energy source. What happens next takes less than a second. Without the outward pressure of nuclear energy release, the iron core collapses under gravity at roughly 1/4 the speed of light. In approximately half a second, a core that was roughly the size of Earth compresses to a sphere approximately 20 kilometers in diameter, the size of a city. The density at the center reaches and exceeds the density of an atomic nucleus, approximately 10 to the power of 17 kilograms per cubic meter. Matter at this density is so compressed that electrons are forced into protons, converting them into neutrons and releasing a flood of neutrinos. A neutron star has formed. The infalling material of the outer core hits the newly formed neutron star and bounces. The neutron star is essentially incompressible, and the shock wave from the bounce travels outward through the infalling material. This shock wave carries more energy than all the light the Sun will emit over its entire 10 billion year lifetime. It tears through the outer layers of the star at tens of thousands of kilometers per second, heating and compressing and eventually blasting the entire stellar envelope, everything above the iron core, outward into space in what is called a core collapse supernova. The supernova of a star like UY Scuti will be visible from Earth with the naked eye, possibly in daylight. At a distance of approximately 9,500 light-years, the peak brightness of the explosion will reach approximately magnitude -6 or 7, brighter than Venus at its brightest, potentially comparable to a crescent moon. For weeks to months, a new star will appear in the constellation Scutum, outshining everything else in the night sky except the moon, visible in broad daylight if the geometry is favourable. This has happened before in recorded history. The supernova of 1054 AD, the event that created the Crab Nebula, was recorded by Chinese and Japanese astronomers as a guest star visible in daylight for approximately 23 days, and visible at night for nearly 2 years. That supernova was approximately 6,500 light-years away. UY Scuti is approximately 9,500 light-years away, farther, which means somewhat dimmer, but still well within the range of naked-eye visibility and potentially daylight visibility at peak brightness. We do not know when this will happen. UY Scuti's remaining lifetime is estimated at perhaps a few 100,000 years, a long time by human standards, geologically brief by stellar standards. It could be tomorrow. There is no physical law preventing it from collapsing tonight, though the probability of it happening on any specific human timescale is vanishingly small. More likely, it will continue its slow evolutionary progression for hundreds of thousands of years, gradually shedding more mass, pulsating, brightening and dimming on its approximately 740-day cycle before the silicon burning phase begins and ends and the core collapses in half a second. When that happens, the information will travel to Earth at the speed of light. Light from the explosion will arrive at Earth approximately 9,500 years after the moment of collapse, because that is how long it takes light to cross the distance, which means the explosion may already have happened. The supernova of UY Scuti may be a fait accompli. The core may have already collapsed. The neutron star may already exist. The shock wave may already have torn through the stellar envelope, and the explosion may be expanding outward through the interstellar medium right now. The light already travelling toward us, 9,000 years into its 9,500-year journey. We would not know. The information has not arrived yet. This is one of the stranger aspects of observational astronomy. The universe we see is not the universe as it currently is. It is the universe as it was at various times in the past, depending on how far away the object is. When you look at UY Scuti through a telescope, you are seeing light that left the star approximately 9,500 years ago, when human civilization was in its earliest stages, before the first cities, before writing, before agriculture had spread across the globe. The star you are looking at may not exist anymore. The giant you are measuring, the pulsations you are tracking, the circumstellar envelope you are imaging, all of it may be historical record. The star itself may be a neutron star, surrounded by an expanding supernova remnant, already 9,000 years into its expansion, visible to anyone in the galaxy who happens to be closer and whose light travel time is already complete. We are observing a past that may already have a present we cannot see. Now consider what the supernova will leave behind. After the explosion tears the outer layers away, what remains at the center depends on the mass of the collapsing core. If the remaining core mass is less than approximately 2 to 3 solar masses, the result is a neutron star, a sphere of neutron degenerate matter approximately 20 kilometers in diameter, spinning rapidly, potentially emitting beams of radio waves as a pulsar. If the core mass exceeds this threshold, the neutron star itself becomes unstable and collapses further, past any known form of matter, past any pressure that physics knows how to resist, into a black hole. For a star with UY Scuti's original mass, approximately 25 to 40 solar masses, the eventual fate is almost certainly a black hole. Not every star in this mass range produces a black hole directly. Some produce neutron stars first. But the mass is large enough that the core remnant likely exceeds the threshold, and the neutron star that briefly forms collapses within fractions of a second of its formation into a black hole with a mass of perhaps 5 to 20 solar masses. This black hole will be small by the standards of the massive black holes at galactic centers, but real in every physical sense. A region of space-time where the gravitational field is so extreme that the escape velocity exceeds the speed of light, where the curvature of space-time is infinite at the singularity, where the normal causal structure of the universe breaks down in ways that general relativity describes mathematically but cannot fully explain physically. The black hole will be invisible in the direct sense. No light escapes from within its event horizon, but detectable through its gravitational influence on surrounding matter and through accretion if material falls into it. It will persist essentially forever on any timescale relevant to stellar astronomy. While stars form and evolve and die around it, while the galaxy continues its slow rotation, while the Sun eventually exhausts its own fuel in approximately 5 billion years, the black hole that was once UY Scuti will still be there, a few solar masses of collapsed space-time drifting through the galaxy, retaining the angular momentum and trajectory of the star that formed it, interacting gravitationally with whatever objects it passes near. The atoms that are not swallowed by the black hole, the vast majority of UY Scuti's mass blown outward in the supernova explosion, will disperse through the interstellar medium over thousands of years, creating a supernova remnant similar to the Crab Nebula or Cassiopeia A, or any of the other supernova remnants visible in our galaxy. The shockwave from the explosion will compress surrounding interstellar gas and dust, potentially triggering the collapse of dense molecular clouds into new stars. The supernova of UY Scuti may, through this shock compression mechanism, be the direct cause of star formation in its neighborhood of the galaxy. The death of the largest star triggering the birth of new stars, the cycle of stellar evolution continuing. This triggering mechanism for star formation is one of the ways that the deaths of massive stars are connected to the births of new stars and new planetary systems. The solar system may itself have formed partly in response to a nearby supernova shockwave, approximately 4.6 billion years ago. There is isotopic evidence in meteorites suggesting that the early solar system was enriched with material from a nearby supernova event that may have contributed to the collapse of the molecular cloud from which the Sun and planets formed. If so, then a dying massive star was part of the cause of the Sun's existence. And through the Sun's existence, of everything in the solar system, including Earth and every living thing on it. The largest stars are not bystanders in the history of the galaxy. They are active participants in its chemical and dynamical evolution, enriching the interstellar medium with heavy elements, triggering star formation through their supernova explosions, seeding the galaxy with the raw materials for planetary systems and for life. A galaxy without massive stars would be a galaxy without the heavy elements necessary for rocky planets, without the supernova explosions that trigger star formation and distribute those elements, without the chemical complexity that eventually gives rise to biochemistry. UY Scuti, for all its exotic extremity, is a representative of a class of objects that are fundamental to why the universe is the way it is. Not numerically, massive stars are rare, comprising a small fraction of all stars, but in terms of their contribution to the chemical and energetic evolution of the galaxy, they are disproportionately important. A single massive star's supernova releases more energy than all the light the sun will emit over its entire lifetime. A single massive star's stellar winds over its lifetime enrich the interstellar medium with more heavy elements than thousands of sun-like stars over their comparable lifetimes. Let us now talk about something that is genuinely uncertain and that represents one of the frontiers of current stellar astrophysics: whether UY Scuti is actually the largest star, or whether it only appears to be because of the specific way we measure stellar sizes and the specific population of stars we have been able to measure. The claim that UY Scuti is the largest known star is accurate as a statement about the current catalogue of measured stellar radii. But that catalogue is incomplete in ways that matter. The Milky Way contains approximately 200 to 400 billion stars. We have measured the radii of a small fraction of them, those that are close enough, bright enough, or large enough in angular size for interferometric measurement. The population of very large stars is biased toward those we can actually measure, which are biased toward those that are nearby in galactic terms. There are candidate stars that have estimated radii comparable to or potentially exceeding UY Scuti, but with larger measurement uncertainties. VY Canis Majoris, another red hypergiant, has estimates ranging from about 1,300 to 2,100 solar radii, depending on the measurement method and assumptions. The uncertainty in VY Canis Majoris's radius is larger than the uncertainty in UY Scuti's, making a comparison uncertain. Stephenson 2-18, a red supergiant in the cluster Stephenson 2, has a recent estimate of approximately 2,150 solar radii, based on indirect methods, larger than the best estimate for UY Scuti, though with significant uncertainty. RSGC1-F01 and other red supergiants in dense stellar clusters near the galactic center may be similarly large, but are difficult to measure because of the dust extinction that makes the galactic center difficult to observe at visible wavelengths. The honest answer to the question of which star is the largest is that we do not know with certainty, and that the competition between the top candidates is within the uncertainties of the measurements. What we do know is that the very largest stars cluster in a size range of approximately 1,500 to 2,200 solar radii, a regime where the physics of red hypergiants pushes stars to the extreme upper boundary of what stellar structure can support. There is a theoretical maximum stellar radius that emerges from stellar physics. Above a certain size, the outer envelope becomes so loosely bound and the radiation pressure so extreme that the star cannot maintain a coherent photosphere. The star's own luminosity drives mass loss at rates that prevent the envelope from growing beyond a certain scale. Different models give somewhat different maximum radii, but they generally cluster in the range of 2,000 to 3,000 solar radii, meaning UY Scuti at approximately 1,700 to 1,900 solar radii is approaching, but not at the theoretical maximum. There may be stars larger than UY Scuti waiting to be measured in the dusty depths of the galactic plane, or in distant stellar clusters where current measurement capabilities are insufficient to determine their sizes precisely. This uncertainty is not a failure of astronomy. It is an honest acknowledgement of the limits of current measurement capabilities applied to objects at the extreme ends of the stellar distribution. The universe does not come with labels. Every number we assign to astronomical objects is the result of a measurement process with specific assumptions, specific uncertainties, and specific limitations. The number 1,708 solar radii for UY Scuti is not a decree from nature. It is the best current estimate from the best current data, subject to revision when better data or better methods become available. This is exactly what happened with UY Scuti's own measured radius in recent years. Early estimates from less precise measurements gave larger radii, up to 2,000 solar radii or more. More careful interferometric measurements combined with better distance estimates revised the number downward to the current approximately 1,700 solar radii. Future measurements with next-generation interferometric facilities, with better distance determinations from astrometric missions, and with improved stellar atmosphere models, may revise it further. The star is not changing. Our ability to measure it is improving. Let us talk about what it means for a star to have a radius of 1,700 solar radii. Not in terms of the numbers, which have already been established, but in terms of the physical character of the star as an astronomical object. Because there is a set of properties that emerge from being this large, that have no analogue in more ordinary stellar physics, and that reveal something genuinely strange about what a red hypergiant actually is. The first is the relationship between the star's size and the speed of sound in its interior. The speed of sound in a gas is related to the temperature and composition of the gas. In the outer envelope of UY Scuti, it is perhaps a few kilometers per second. The sound crossing time, the time it takes a sound wave to travel from one side of the star to the other, is approximately years to decades. In the Sun, the sound crossing time is approximately 2 hours. The entire structure of the Sun communicates with itself acoustically on a timescale of hours. UY Scuti communicates with itself acoustically on a timescale of years. This has profound consequences for the star's dynamics. Perturbations, pressure waves, convective disturbances, pulsational modes take years to propagate from one side of the star to the other. The star cannot respond to disturbances quickly in the way that smaller, denser stars can. Its enormous size makes its response slow, its equilibration gradual. This is part of why the pulsational period of UY Scuti is approximately 740 days. The star is literally oscillating on its acoustic timescale, the natural resonant frequency of its enormous size. The surface gravity of UY Scuti is also dramatically different from the Sun's. The surface gravity of a star scales as mass divided by radius squared. UY Scuti has approximately 7 to 10 solar masses, but a radius of approximately 1,700 solar radii. The surface gravity is therefore approximately 7 divided by 1,700 squared, roughly 2 to 3 orders of magnitude less than the Sun's surface gravity. A person standing on UY Scuti's photosphere, if that were physically possible in any sense, would experience gravity so weak that they would weigh less than they would in most laboratory vacuum systems on Earth. The photosphere of UY Scuti is barely gravitationally bound. It is a tenuous, loosely organized layer of gas held in place by a gravitational force so weak that the radiation pressure from the stellar interior is nearly sufficient to blow it away entirely. This near balance between gravity and radiation pressure at UY Scuti's surface is why the mass loss rate is so extreme. The ratio of radiation pressure to gravitational force, called the Eddington ratio, approaches unity at UY Scuti's luminosity and surface gravity. When the Eddington ratio reaches 1, the radiation force exactly balances gravity, and the star can no longer hold its outer layers at all. UY Scuti is not quite at this limit. If it were, it would be blowing itself apart catastrophically rather than shedding mass at the high but not catastrophic rate it actually maintains. But it is close enough that its outer envelope is in a perpetual state of near escape, constantly being accelerated outward, periodically detached in large-scale mass loss events, maintained against complete dispersal only by the marginal excess of gravity over radiation pressure. The circumstellar envelope that results from this mass loss is a remarkable structure in its own right. It is not simply a diffuse haze of expelled material. It has structure, knots and arcs and shells produced by variations in the mass loss rate over time, by interactions between faster and slower outflow, by the influence of convective cells on the wind launching mechanism. High-resolution imaging of UY Scuti and similar stars shows the circumstellar envelope as a complex, asymmetric structure with distinct morphological features that record the history of the star's mass loss episodes. The dust in this circumstellar envelope is particularly important. At the temperatures in the outer envelope and wind, a few hundred to a few thousand Kelvin, silicate and carbon-based dust grains can condense from the gas. These dust grains are efficient absorbers and emitters of infrared radiation. They intercept photons from the star and re-radiate them at longer wavelengths, which is why UY Scuti appears much brighter in the infrared than in visible light, and why observations of stars like UY Scuti prefer infrared wavelengths that can penetrate the dust, rather than visible wavelengths that are absorbed and scattered by it. The dust grains are also important for the mass loss mechanism itself. Radiation pressure acts more effectively on dust grains than on gas molecules, because dust grains have larger cross-sections for absorbing photons. The radiation pressure on the dust grains accelerates them outward, and the dust then drags the surrounding gas along through collisions, driving the wind even in regions where the radiation pressure on the gas alone would be insufficient to overcome gravity. This dust-driven wind is the dominant mass loss mechanism for cool, evolved stars like UY Scuti, and it is responsible for the high mass loss rates that are depleting the star's envelope and driving its rapid evolution. The chemistry of the dust and the chemistry of the gas in the circumstellar envelope depend on whether the star is oxygen-rich or carbon-rich, determined by the relative abundances of carbon and oxygen in the envelope, which in turn depend on the nuclear burning history and the degree of mixing between the core and envelope. In oxygen-rich envelopes, oxygen atoms bind with silicon and other elements to form silicate dust grains, the same mineral chemistry found in Earth's rocks and in the rocky planets of the solar system. In carbon-rich envelopes, carbon atoms form graphite grains and complex organic molecules, including polycyclic aromatic hydrocarbons, large carbon ring molecules found throughout the interstellar medium and implicated in prebiotic chemistry. UY Scuti is classified as an oxygen-rich star. Its envelope contains more oxygen than carbon, producing primarily silicate dust. The silicate grains condensing in UY Scuti's circumstellar envelope are being expelled into the interstellar medium, where they will eventually be incorporated into molecular clouds, into protoplanetary disks, into the rocky planets of new solar systems forming elsewhere in the galaxy. The silicon and oxygen atoms in those future rocky planets will carry the chemical signature of their origin in a red hypergiant's circumstellar envelope, chemically indistinguishable from silicon and oxygen atoms that formed in any other stellar environment, but physically having passed through the most extreme large-scale stellar structure in the galaxy. There is another aspect of UY Scuti that receives less attention in popular discussions, but that is scientifically significant: its variability. UY Scuti is not a simple periodic variable star with a clean, predictable light curve. It is a semi-regular variable, which means its brightness changes on multiple timescales with overlapping periodicities and significant cycle-to-cycle variation. The approximately 740-day period is the dominant variability, but superimposed on this are shorter period variations, longer period trends, and irregular fluctuations associated with the stochastic nature of convection in the outer envelope. This variability is scientifically important because it encodes information about the stellar interior. Different pulsational modes, different ways the star can oscillate, have different periods and different spatial patterns of brightness variation. Analyzing the mixture of periods in a star's light curve provides constraints on the stellar structure, the density profile, the temperature profile, the opacity of different layers, in ways that complement and extend the information available from spectroscopy and interferometry. This technique, called asteroseismology when applied to solar-like oscillations, and asteroseismology of evolved stars when applied to more complex cases, is one of the primary tools for probing the interiors of stars that cannot be directly sampled. For red hypergiants like UY Scuti, the asteroseismological analysis is complicated by the fact that convection is not a perturbation on an otherwise smooth stellar structure. It is a dominant feature that contributes to the variability on comparable timescales as the pulsational modes. Separating the convective variability from the pulsational variability requires long baselines of monitoring and sophisticated analysis techniques. Studies of UY Scuti and similar stars are ongoing, and the data being accumulated by current and future photometric monitoring programs will eventually allow constraints on the stellar interior that are not currently available. The specific value of these measurements goes beyond understanding UY Scuti in isolation. The physics of red hypergiants is one of the less well-constrained areas of stellar evolution theory. The uncertainties in the treatment of convection, mass loss, and the interaction between pulsation and mass loss in stellar evolution models are large enough that different model codes produce significantly different predictions for the evolutionary tracks, lifetimes, and final fates of massive stars. Observations of specific red hypergiants like UY Scuti provide empirical constraints that can discriminate between different model assumptions and improve the accuracy of stellar evolution theory across a range of masses and evolutionary states. Better stellar evolution models have consequences for cosmology and galaxy evolution. because the chemical enrichment of galaxies by stellar mass loss and supernova explosions is one of the key inputs to models of galaxy formation and evolution. Getting the stellar evolution right is a prerequisite for getting the galaxy evolution right. UY Scuti, as the most extreme example of the red hypergiant class, provides the most stringent test of stellar evolution theory in this regime. The most extreme object produces the most stringent constraints, because a theory that fails to reproduce the most extreme case is definitively ruled out for that regime, even if it succeeds for more moderate cases. Consider now what UY Scuti tells us about the upper boundary of stellar physics. Not just the upper boundary of stellar size, but the upper boundary of what a star can be while still being a star in the conventional sense. The Humphreys-Davidson limit, mentioned earlier, defines an empirical boundary in the Hertzsprung-Russell diagram above which very few stars are found. Specifically, luminous hot stars are absent above this limit, and the very luminous cool stars that do exist above or near it are transient. They are passing through this region rapidly in evolutionary terms, not residing there. The physical cause of the Humphreys-Davidson limit is the approach to the Eddington luminosity, the luminosity at which radiation pressure balances gravity for a given mass. For the most massive stars, those above approximately 40 to 60 solar masses, the Eddington luminosity is reached while the star is still on the main sequence or in the early post-main sequence phase. Such stars cannot evolve calmly to the red supergiant stage because they would exceed the Eddington luminosity during that evolution. Instead, they lose mass so rapidly at intermediate temperatures that they never fully expand to become red supergiants. They spend time as luminous blue variables, highly unstable, episodically mass-losing stars, or as Wolf-Rayet stars that have shed their entire hydrogen envelope and exposed their bare helium-burning cores. UY Scuti exists as a red hypergiant because its mass, while large, was not so large that it exceeded the Eddington luminosity before evolving to the cool giant phase. It started with perhaps 25 to 40 solar masses, evolved off the main sequence, expanded to hypergiant dimensions, and is now shedding mass at an extreme rate as it approaches the conditions that will eventually trigger its final collapse. The specific evolutionary path that produces a red hypergiant rather than a luminous blue variable or Wolf-Rayet star is determined by a combination of initial mass, initial rotation rate, metallicity, and the specific prescriptions for convective mixing and mass loss that stellar evolution models use, all of which have significant uncertainties. This means UY Scuti is not just a large object, it is a diagnostic of the physics that determines which massive stars become which types of evolved objects. A question with implications for the entire statistical distribution of stellar evolutionary endpoints in the galaxy. Every time a massive star explodes as a supernova, the type of supernova, the properties of the compact remnant, and the chemical yield depend on the evolutionary path the star took, which depends on the physics that UY Scuti and its cousins are constraining. Let us now step back from the specific details and look at UY Scuti from the perspective of someone trying to understand their place in the universe. Not a scientist with specific measurements to analyze, but a person who wants to understand what it means that an object like this exists. It exists approximately 9,500 light-years from Earth. That means the light arriving at your telescope from UY Scuti tonight left the star approximately 9,500 years ago, when human civilization was just beginning, when the first cities were being built in Mesopotamia, when writing had not yet been invented, when the entire accumulated knowledge of science did not exist. The light that allows you to measure the star's angular diameter, pulsational period, surface temperature, and chemical composition has been travelling through interstellar space since before any of those measurements were conceptually possible. The star it left is 1,700 times the radius of the Sun. The Sun is 109 times the radius of Earth, so UY Scuti is approximately 185,000 times the radius of Earth. The sphere it occupies in space has a volume approximately 6.3 times 10 to the 15th times the volume of Earth. That is 6 quadrillion Earths by volume. The number is so large it has essentially no meaning as a number. It just is the number, sitting there, incomprehensible but accurate. And it is one star, one object. There are approximately 200 to 400 billion stars in the Milky Way galaxy. UY Scuti is one of them. There are approximately 1 to 2 trillion galaxies in the observable universe. Each of them contains comparable numbers of stars. The observable universe may contain something in the range of 10 to the 24th stars, a septillion stars. And UY Scuti is one of them, one of the largest, sitting 9,500 light-years away in a minor constellation near the galactic centre, pulsating on a 740-day cycle, shedding millions of times more mass per year than the Sun, approaching the end of an existence that has lasted millions of years and will end in a collapse that takes half a second. There is a specific kind of vertigo that comes from holding these numbers in mind simultaneously, the number that represents UY Scuti's size and the number that represents how many objects like it exist in the universe. Not exactly like it. Red hypergiants are rare. Perhaps 1 in a million stars reaches this evolutionary stage. But stars of every description, burning at every temperature and luminosity in various stages of their evolution, distributed across the volume of a universe so large that the distance to UY Scuti, 9,500 light-years, represents a negligible fraction of even our local galaxy. The human response to this is interesting to examine. Most people, when confronted with numbers of this magnitude, experience a kind of cognitive shutdown. The numbers are processed as symbols that indicate largeness without producing any genuine intuition for what the largeness means. The mind retreats to familiar scales. The numbers remain numbers rather than becoming realities. This is not a failure of intelligence, it is a property of how human cognition works. Our nervous systems evolved to navigate a world where the relevant scales range from centimeters to kilometers, the scale of objects you can touch or walk to. The scale of stars and galaxies and cosmological distances is not one that natural selection produced any cognitive apparatus for processing intuitively. The number 9,500 light-years does not feel like anything in the way that 9,500 meters feels like something, like a long walk, like a distance you could traverse in a day, like something that has physical reality in your experience. What astronomy asks you to do, what looking at UY Scuti honestly requires, is to accept numbers that cannot be made intuitive, to hold them as accurate descriptions of reality, even though they produce no corresponding experiential resonance. To know that UY Scuti is 1,700 solar radii across without feeling what that means, and to accept that the feeling is not available, that the scale is genuinely beyond human intuition, while still taking the knowledge seriously as a description of what is actually there. This is a form of intellectual humility that is specific to confronting astronomical scales. It requires acknowledging the limits of your own perceptual apparatus, while trusting the measurement process that produced the numbers. The numbers are right, even though they feel like nothing. The star is that large, even though you cannot experience what that largeness means. The universe is that old and that vast and that populated with objects of this extraordinary character, even though none of that is accessible to intuition. And sitting with that, with the knowledge that accurate descriptions of reality can be completely inaccessible to experience, is itself a kind of understanding. Not understanding of UY Scuti specifically. Understanding of the relationship between human cognition and the universe it exists within, a universe that did not scale itself to human experience, that operates across ranges of size and time and energy that dwarf anything in the environment that shaped human perception. UY Scuti did not form for us to look at. It did not evolve to its hypergiant phase as part of any story about human significance or insignificance. It formed because the laws of physics, specifically the laws governing the collapse of dense molecular clouds under gravity and the subsequent nuclear burning of the resulting stellar object, operated in a specific location in the Milky Way approximately tens of millions of years ago, and produced an object with specific initial conditions that have evolved to produce the current red hypergiant. The process was indifferent to whether anyone would ever observe it, and yet we observe it. And the observation, the measurement of its angular diameter by interferometry, the analysis of its spectrum, the modelling of its interior structure and evolutionary state, is itself a remarkable thing. A species that evolved on a small rocky planet orbiting an unremarkable star developed the intellectual and technological capacity to measure the angular diameter of a star 9,500 light-years away to a precision of a few percent, to determine its surface temperature from the spectral distribution of its emitted light, to infer its interior structure from the analysis of its pulsational periods, to calculate its evolutionary history from the application of nuclear physics and thermodynamics and fluid dynamics coded into stellar evolution models. That capacity, the capacity to look at a point of light in the sky and determine from the light alone what the object is, how it works, where it came from, and where it is going, is one of the extraordinary achievements of human science. It required centuries of accumulated theoretical and observational work. It required the development of spectroscopy and interferometry and photometry, and the theoretical framework of stellar structure and evolution. It required the recognition that the laws of physics operating in terrestrial laboratories also operate in stellar interiors 9,500 light-years away. A recognition that is not obviously true and that was genuinely controversial at various points in the history of science. The universality of physical law, the fact that the same equations that describe nuclear reactions in terrestrial accelerators also describe nuclear reactions in stellar cores, the same fluid dynamics that describes laboratory convection also describes convection in stellar envelopes. The same gravity that holds objects to Earth's surface also determines the structure and evolution of the most extreme stars, is the foundation on which all of astrophysics rests. It is not something that was known in advance. It was discovered empirically, confirmed repeatedly, and is now so well established that it is taken for granted. But it is a discovery, a fundamental fact about the universe, not an obvious truth. UY Scuti is what it is because the same physics that operates in laboratories on Earth also operates in stellar environments that differ from those laboratories by many orders of magnitude in temperature, density, pressure, and spatial scale. The fact that we can understand UY Scuti at all that the measurements make sense, that the models reproduce the observations, that the star behaves in ways that the equations predict, is evidence for the universality of physical law operating across the full range of the universe's physical conditions. That universality is remarkable. The universe did not have to work that way. The laws of physics could have been different in different places or at different scales. They are not. The same mathematics describes hydrogen fusion in a stellar core and hydrogen fusion in a laboratory experiment. The same fluid dynamics describes convective cells in a pot of boiling water and convective cells in the envelope of a red hypergiant. The same gravity describes the fall of an apple and the collapse of an iron stellar core. UY Scuti, in this sense, is not just an extreme object. It is a test of physical law at extreme conditions, a natural experiment conducted at scales and in regimes that no laboratory could reproduce, confirming that the laws hold where we cannot directly intervene, that the universe is self-consistent across the full range of its physical diversity, that the same principles that operate at human scales also operate at the scales where the largest stars burn and collapse and seed the galaxy with the elements of which planets and people are made. There is a specific moment in the history of human understanding of stars that is worth dwelling on, not because it is the most dramatic moment, but because it is the most revealing about how science actually works when confronted with objects that exceed everything previously known. For most of human history, stars were lights, points of fire fixed in a celestial sphere, eternal and unchanging by definition, categorically different from the matter of the terrestrial world. Aristotle taught that the heavens were made of a fifth element, the quintessence, fundamentally unlike the four elements of earth, water, fire, and air that composed everything below the moon. The celestial realm was perfect and immutable. The terrestrial realm was imperfect and changeable. The boundary between them was absolute. This framework survived for roughly 2,000 years, not because people were unintelligent. The ancient Greeks and the Islamic scholars and the medieval European astronomers who worked within this framework were extraordinarily intelligent by any measure. It survived because it was consistent with the observations available. Stars looked fixed and eternal. The mathematics of celestial motion worked without requiring the heavens to be made of ordinary matter. There was no observational pressure to abandon the framework because no observation seemed to contradict it in any decisive way. Then, in 1572, a new star appeared in the constellation Cassiopeia. Tycho Brahe, the most precise naked-eye observer in the history of astronomy, working before the invention of the telescope, measured its position night after night and found that it showed no parallax, no shift against the background stars as Earth moved. This meant it was not a nearby atmospheric phenomenon. It was far away, in the realm of the fixed stars, in the supposedly immutable celestial sphere. And it had not been there before, and it faded over months and disappeared. The celestial sphere was not immutable. Stars could appear and disappear. Something could change in the heavens. The conceptual framework that had organized human understanding of the cosmos for 2 millennia was wrong in a fundamental way. What Tycho observed was a supernova, the explosion of a massive star at the end of its life. He did not know that. He had no framework for understanding what it was. He simply measured it carefully, recorded what he saw, and drew the conclusion that the evidence required, that the heavens were not the unchanging realm of perfect quintessence, but a physical place where things happened, where objects could be born and die, where the same universe that produced earthquakes and thunderstorms on Earth also produced dramatic changes at stellar distances. That observational honesty, the willingness to follow the evidence to a conclusion that contradicted the most authoritative intellectual framework of his time, is the same intellectual virtue that is required today when confronting objects like UY Scuti. The numbers UY Scuti produces are not intuitive. They do not fit comfortably into any experiential framework. They contradict, in a different way, the implicit assumption that stars are objects of comprehensible size, operating in comprehensible ways. UY Scuti is not comprehensible in the intuitive sense. And acknowledging that, accepting the numbers as accurate without pretending they feel like anything, is the modern version of Tycho's observational honesty. The parallels extend further. Tycho's supernova was later understood, centuries later when the physics became available, to be the endpoint of stellar evolution for a massive star. The object Tycho saw was the same type of event that UY Scuti will eventually produce. The same physics, the same sequence of nuclear burning stages ending in iron core collapse, the same shock wave tearing through the stellar envelope, the same burst of light visible across the galaxy. Tycho did not know this. He could not have known it. The nuclear physics that explains stellar evolution was not developed until the 20th century, nearly 400 years after Tycho's observation. But Tycho's observation was necessary for the development of that understanding. Without the observational demonstration that the heavens were not immutable, the conceptual framework that eventually allowed stellar evolution to be understood could not have developed. The observation preceded the understanding by 400 years. The person who made the observation never knew what they were actually seeing. This is a pattern in the history of science that repeats itself with remarkable consistency. Observations made without the theoretical framework to interpret them correctly are recorded, archived, puzzled over, and eventually understood when the theory catches up. The understanding may come decades or centuries after the observation. The observer may be long dead. The data they collected, the careful measurements, the precise positions, the recorded timings, survive to be reinterpreted in light of theories that were not yet imagined when the data were taken. The data being collected on UY Scuti right now, the interferometric measurements of its angular diameter, the spectroscopic measurements of its atmospheric composition and velocity fields, the photometric measurements of its pulsational variations, the infrared measurements of its circumstellar envelope, will be available to future astronomers working with theoretical frameworks not yet developed. Some of what is being measured now will turn out to be evidence for physical processes not yet understood. Some measurements that currently seem straightforward will prove, in hindsight, to have been encoding information about phenomena that current theory does not predict. This is not speculation about a distant possibility. It is the routine experience of science in every field. Data collected for one purpose routinely turns out to contain information about something else entirely, information that was in the data all along, but that required a theoretical framework developed later to recognize and interpret. The history of astronomy is full of examples. Measurements of stellar proper motions that turned out to encode information about the rotation of the galaxy. Observations of Cepheid variable stars that turned out to be cosmic distance indicators. Measurements of galaxy recession velocities that turned out to be evidence for the expansion of the universe. UY Scuti is being observed now with the best available instruments by scientists who are asking specific questions based on current theoretical understanding. Future scientists, working with better instruments and better theory, will ask different questions of the same data and find answers to questions that current science does not yet know to ask. Now consider the population context, where UY Scuti sits in the distribution of stellar masses and sizes across the galaxy, and what that distribution tells us about the stellar physics that produced it. The mass function of stars, the distribution of stellar masses at birth, is a power law. More precisely, it approximates the salpeter initial mass function, first characterized by Edwin Salpeter in 1955, which describes the number of stars born per unit mass interval as approximately proportional to mass to the power of negative 2.35. This means that for every star born with a mass greater than 10 solar masses, approximately 300 stars are born with masses between 1 and 10 solar masses. And for every star with a mass greater than 40 solar masses, thousands of lower mass stars are born in the same stellar population. Massive stars are rare. They are rare in the specific mathematical sense that the initial mass function strongly favors low-mass stars. The Sun is not a typical star. It is actually somewhat more massive than the median stellar mass, which is closer to about half a solar mass. Stars with masses in the range that eventually produce red hypergiants, roughly 25 to 40 solar masses and above, constitute perhaps 1 in 10,000 stars formed. Their visual prominence in the night sky, despite their rarity, is a consequence of their extraordinary luminosity. A single red hypergiant, like UY Scuti, can outshine hundreds of thousands of Sun-like stars, making it visible at distances that Sun-like stars at the same location would be invisible. This luminosity bias affects our census of the stellar population. When we look at the night sky or catalogue the stars in our galaxy, we see a population biased toward the most luminous objects. The intrinsically faint stars, the red dwarfs that constitute the majority of stellar mass in the galaxy, are mostly invisible to the naked eye and underrepresented in pre-space age stellar catalogues. The brilliant blue supergiants and red hypergiants are vastly overrepresented relative to their true numerical frequency. The population of stars that shaped human knowledge of astronomy for centuries is not a representative sample of the galaxy's actual stellar population. This matters for understanding UY Scuti's place in the broader picture. It is exceptional in almost every measurable dimension: size, luminosity, mass loss rate, evolutionary rate, proximity to the Eddington limit. And it is exceptional partly because the physics of stellar evolution selects for extreme properties in the small fraction of stars that reach the red hypergiant stage. But it is also the object that draws our attention precisely because it is extreme. Its size and luminosity make it detectable and measurable at distances where less extreme objects would be invisible or unmeasurable. The population of red hypergiants in the galaxy is small but not negligible. Estimates suggest the Milky Way contains perhaps a few dozen to a few hundred red hypergiants at any given time. Rare because the evolutionary phase is short and because only the most massive stars reach it, but present throughout the galaxy in regions of active star formation where massive stars are born and evolve on short timescales. The galactic center region, the spiral arms where molecular clouds are dense and star formation is ongoing, the massive stellar clusters scattered through the disk. These are the environments where red hypergiants preferentially exist. Several of the most well-studied red hypergiants, UY Scuti, VY Canis Majoris, Mu Cephei, W Persei, RW Cephei, are at different evolutionary stages within the red hypergiant phase. Some are pulsating vigorously. Some show evidence of recent large-scale mass loss events in the structure of their circumstellar envelopes. Some are apparently more stable, and some are apparently more variable. Comparing the properties of these different objects provides a kind of statistical sample of the red hypergiant phase at different moments, allowing stellar evolution models to be tested against the observed range of properties rather than against just a single object. UY Scuti, as the apparently largest, sits at the extreme of this sample. Its properties define what the red hypergiant phase looks like when pushed to its maximum extent. The theoretical framework that describes UY Scuti must also describe the less extreme members of the class, and a theory that gets UY Scuti right but fails for Mu Cephei, or gets Mu Cephei right but fails for UY Scuti, is telling us something important about the range of physical conditions that the theory handles correctly and incorrectly. Let us examine something that popular discussions of UY Scuti almost never address: the chemical composition of the star and what it tells us about both its own history and the broader chemical evolution of the galaxy. UY Scuti is not made of the same material as the Sun. More precisely, it contains the same fundamental elements but in different proportions, and those proportions reflect a history that is different from the Sun's history in important ways. The Sun formed approximately 4.6 billion years ago from a molecular cloud whose composition reflected the chemical enrichment of the galaxy up to that point. The galaxy was already approximately 9 billion years old when the Sun formed. 9 billion years of stellar evolution. 9 billion years of massive stars forming, burning, and expelling their processed material into the interstellar medium, gradually enriching the galaxy's gas with carbon, nitrogen, oxygen, silicon, iron, and all the heavier elements that stellar nucleosynthesis produces. UY Scuti is much younger than the Sun, tens of millions of years old rather than billions. It formed more recently from molecular cloud material that had experienced an additional several billion years of chemical enrichment compared to the cloud that formed the Sun. Its initial composition was therefore richer in heavy elements than the Sun's initial composition, a consequence of forming later in the chemical evolution of the galaxy. This matters for stellar evolution because metallicity, the astronomical term for the abundance of elements heavier than helium, affects stellar structure and evolution in multiple ways. Higher metallicity increases the opacity of stellar material to radiation, affecting how energy is transported through the stellar interior. It affects the efficiency of mass loss through stellar winds, because the radiation pressure that drives mass loss acts more effectively on material with higher metal content, more elements with more complex electron structures that absorb photons more efficiently. And it affects the nucleosynthetic yields of the eventual supernova, determining which elements are produced in which quantities and expelled into the interstellar medium. A higher metallicity star, like UY Scuti, therefore loses mass more efficiently through its stellar wind than a lower metallicity star of the same initial mass would. This affects its evolutionary track, the specific path it follows on the Hertzsprung-Russell diagram, and the properties it has when it reaches the red hypergiant phase. Stars that form in the early universe from metal-poor gas follow different evolutionary paths than stars forming today from gas enriched by billions of years of prior stellar evolution. Understanding UY Scuti requires understanding where it fits in the galaxy's chemical evolution timeline. And understanding the galaxy's chemical evolution requires understanding objects like UY Scuti that are the primary drivers of that evolution. The iron that will be produced in UY Scuti's core in the final silicon burning phase will not escape the star. Iron cores collapse rather than being expelled. But everything above the iron core will be blown outward in the supernova, seeding the surrounding interstellar medium with carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, and a range of heavier elements produced in the stellar interior and in the supernova explosion itself. The supernova nucleosynthesis, the nuclear reactions that occur in the explosive shock wave propagating through the stellar layers during the supernova, produces elements that stellar burning alone does not efficiently produce. Radioactive nickel-56, which decays to cobalt-56 and then to stable iron-56, is produced in large quantities in core collapse supernovae and powers the light curve of the supernova during the weeks and months after the explosion. The gamma rays from this radioactive decay, converted to visible and infrared light by the expanding envelope, are what makes the supernova visible across galactic distances. Heavier elements, strontium, barium, the rare earth elements and others, are produced in processes that require an intense flux of neutrons to build nuclei heavier than iron through successive neutron captures. Two types of processes contribute. The slow neutron capture process, or S process, operates during the late stages of stellar evolution in certain shell-burning regions, producing elements up to bismuth. The rapid neutron capture process, or R process, requires neutron fluxes so extreme that they only occur in environments like core collapse supernovae, or neutron star mergers, producing elements including the heaviest naturally occurring elements like uranium and thorium. The specific mix of heavy elements produced by UY Scuti's eventual supernova will depend on the details of the explosion energy, the mass cut between the material that falls into the compact remnant and the material that is ejected, the neutron richness of the ejector, the degree of mixing between different compositional layers during the explosion. These details are not fully predictable from current supernova models, which is one of the frontiers of computational astrophysics, simulating core collapse supernovae from first principles with sufficient detail to predict the chemical yields accurately. The challenge is the physics. Core collapse supernova simulations must simultaneously handle the extreme nuclear physics of the collapsing iron core, the neutrino transport that carries away most of the explosion energy, the magnetohydrodynamics of the shock wave propagating through stratified stellar layers, the nucleosynthesis of dozens of isotopes in the explosive burning, and the large-scale hydrodynamics of the expanding ejector. All of these processes coupled together, operating over timescales ranging from milliseconds in the core collapse to years in the ejector expansion, in a three-dimensional geometry that resists simplification. Current supercomputer simulations can reproduce many features of observed supernovae, but still struggle with some aspects of the explosion mechanism itself. Specifically, how the shock wave that bounces off the neutron star gains enough energy to continue expanding outward, rather than stalling and falling back onto the neutron star. Neutrino heating, the absorption of a small fraction of the enormous neutrino flux from the cooling neutron star by the material behind the shock, is the leading mechanism, and simulations with sophisticated neutrino transport do show successful explosions in many cases. But the details of why some simulations explode and others do not, and how the explosion properties depend on the progenitor star's structure, are still active research questions. UY Scuti's specific progenitor structure, the density and composition profiles of its nested shells of nuclear burning, the mass of its iron core when collapse occurs, the structure of its envelope, will determine the specific properties of its eventual explosion. That structure is evolving right now, on the timescale of the current nuclear burning phases. The silicon burning phase that will end in core collapse is perhaps hundreds of thousands of years in the future for UY Scuti, or, as noted, perhaps already in the past, with the light from the explosion still travelling toward us. Either way, the atoms that will eventually be expelled from UY Scuti's supernova are currently inside the star, participating in the nuclear burning and convective mixing that is processing them into their final pre-explosion composition. The oxygen that will eventually seed future stellar systems with the raw material for rocky planets is right now in the oxygen-burning shell of UY Scuti's interior, being produced by carbon burning and awaiting the explosive dispersal of the supernova. The silicon that will become the silicon in future planetary crusts is right now in the silicon-burning shell, approaching its final transformation into iron. This is the connection between the largest star and the smallest chemistry, between the billion-kilometer radius object pulsating in scutum and the molecular complexity of life on Earth. The atoms in living organisms were once inside stars like UY Scuti. Not this specific star. The Sun formed from material expelled by stars that lived and died before the solar system formed. Not from material being expelled by UY Scuti today. But the process is the same. Massive stars burn, expel, collapse, and seed the galaxy. The atoms pass through stellar interiors and emerge enriched, complexified, processed from the simple hydrogen and helium of the early universe into the chemical diversity of the periodic table. And eventually they end up in planets, and in the organisms on those planets, in the carbon of organic molecules, in the oxygen carried by hemoglobin, in the calcium of bones, in the phosphorus of DNA. You are chemically downstream of stars like UY Scuti, not this star specifically. But this class of object, the red hypergiants and their supernova explosions, are part of the chain of processes that produce the atoms you are made of. The largest stars are not separate from life. They are causally connected to it, through the nuclear physics of stellar interiors, through the dynamics of supernova explosions, through the dispersal of processed material into molecular clouds, through the formation of new stellar systems from that enriched material. This connection does not make the universe friendly or intentional or designed with life in mind. UY Scuti does not know about life. The supernova that will eventually produce the atoms that will eventually find their way into future organisms on future worlds is not aimed at those organisms. It is a physical process following physical laws with complete indifference to its downstream consequences. But the connection is real. And knowing that it is real, knowing that the object pulsating in scutum on a 740-day cycle is part of the causal chain that produced every living thing that has ever existed on Earth, changes how the number 1700 solar radii feels. Not making it smaller, not making it more intuitive, not bringing it within the range of human experiential scale, but giving it a meaning that goes beyond its magnitude. It is not just large, it is large in a way that is connected to everything small. That connection between the largest scales and the smallest, between the red hypergiants and the biochemistry of living cells, is one of the genuine insights of 20th and 21st century astrophysics. It was not obvious in advance. It required the development of nuclear physics to understand stellar energy sources, the development of spectroscopy to measure stellar compositions, the development of stellar evolution theory to trace how compositions change through stellar lifetimes, and the development of cosmochemistry to identify the stellar origin of specific isotopes in terrestrial and meteoritic samples. Each step required both theoretical development and observational confirmation. The theory of stellar nucleosynthesis, developed primarily by Hans Bethe, Fred Hoyle, William Fowler, and Margaret and Geoffrey Burbidge in the 1940s and 50s, predicted that the elements heavier than lithium were produced in stellar interiors. The observational confirmation came from multiple directions simultaneously. Spectroscopic measurements of stellar compositions showing the products of nucleosynthesis, measurements of isotopic abundances in meteorites showing signatures of specific nucleosynthetic processes, eventually direct detection of gamma rays from radioactive isotopes in supernova ejecta, confirming that supernova nucleosynthesis was actually occurring. The connection between stellar evolution and the chemical composition of life is now as well established as any fact in astrophysics. The specific isotopic ratios in the atoms of your body carry fingerprints of the stellar processes that produced them, fingerprints that cosmochemists can read in carefully analyzed samples to trace the origin of specific atoms to specific types of stellar environments. Some of the atoms in your body carry isotopic signatures of S-process nucleosynthesis in asymptotic giant branch stars. Some carry R-process signatures from neutron star mergers or supernovae. Some carry signatures of cosmic ray spallation, the fragmentation of heavier nuclei by energetic cosmic ray particles in the interstellar medium. Your body is not made of one type of stellar material. It is made of a mixture from multiple stellar sources, processed and mixed in the interstellar medium over billions of years, concentrated into the molecular cloud that formed the solar system, differentiated into the rocky planet Earth, cycled through geological and biological processes, and ultimately assembled into the specific molecular architecture of a living organism. This history is written in the atoms. It is not accessible to human perception. You cannot feel the provenance of specific atoms in your body, but it is there, encoded in isotopic ratios that measuring instruments can read. And it connects you in a chain of physical causation stretching across billions of years and billions of light years to objects like UY Scuti, the largest star we know, pulsating in the constellation Scutum, currently shedding millions of times more mass per year than the Sun, approaching the end of an existence that began tens of millions of years ago in the gravitational collapse of a dense molecular cloud. There is one more aspect of UY Scuti that deserves careful attention. Not its size or its evolutionary state or its eventual fate, but its location, and what that location tells us about the environment in which the most extreme stellar evolution occurs. UY Scuti sits in the constellation Scutum, which lies toward the center of the Milky Way galaxy as seen from Earth. It is at a distance of approximately 9,500 light-years, which places it in the region of the galaxy between Earth's position and the galactic center, in the inner disk where the density of stars, gas, and molecular clouds is higher than in the outer disk where the Sun resides. This location is not coincidental. Massive stars form preferentially in regions of high gas density, in the giant molecular clouds that are concentrated in the spiral arms and toward the galactic center. The inner galaxy has more molecular cloud material, more active star formation, more massive stars. The outer galaxy, where the Sun is quieter, less star formation, fewer massive stars, a less chemically enriched interstellar medium. UY Scuti is a product of the inner galaxy's more active stellar environment. The molecular cloud from which it formed was likely denser, more massive, and more chemically enriched than the cloud from which the Sun formed. The star-forming region that produced UY Scuti may have simultaneously produced dozens or hundreds of other massive stars. Because molecular cloud collapses in high-density regions tend to produce clusters of stars spanning a range of masses, with a few massive members and many lower mass members formed from the same parent cloud. The cluster that produced UY Scuti, if there was one, may have largely dispersed over the tens of millions of years since the star formed. Massive stars evolve quickly, and the supernovae of the most massive members of a stellar cluster can disrupt the remaining cluster stars and gas over a few million years, leaving a scattered population of stars moving through the galaxy with similar velocities, but no longer gravitationally bound. UY Scuti may be a solitary survivor of a stellar nursery that has dispersed, the last massive member of a birth cluster whose other members have already evolved and died. Or it may be in a cluster that is still identifiable. There are massive stellar clusters in the inner galaxy where red supergiants and hypergiants are concentrated. The cluster Stephenson 2, also called RSGC2, contains several red supergiants, including stars with estimated radii comparable to UY Scuti. The cluster RSGC1 contains similarly extreme objects. These clusters are in the inner galactic disk in the same general region as UY Scuti, and they represent the most extreme stellar environments in the Milky Way, regions where the most massive stars that the galaxy currently produces are in their final evolutionary stages, collectively enriching the surrounding interstellar medium with the processed material from their winds and, eventually, their supernovae. The inner galaxy is therefore, in a real sense, the most chemically active region of the Milky Way, the region where the most massive stars are burning most rapidly, expelling the most material, and eventually exploding in supernovae that drive the chemical evolution of the surrounding interstellar medium at rates far exceeding anything in the outer galaxy. The atoms being expelled from UY Scuti's surface today will, in millions of years, be incorporated into new molecular clouds forming in the inner galaxy, and from those clouds into new stars with higher metal content than the stars of the current generation, and from those stars into rocky planets with more available heavy elements than the planets of the current generation. The galaxy is evolving chemically on timescales of billions of years, and UY Scuti is one of the current contributors to that evolution, one node in a network of massive stars that are, together, slowly transforming the composition of the galaxy's interstellar medium, from the hydrogen and helium-dominated mixture of the early universe toward the metal-rich mixture that will characterize future generations of stars and planets. On the timescale of the universe's history, 13.8 billion years and counting, the chemical evolution of galaxies is one of the dominant physical processes determining what the universe is like today versus what it was like in its early phases. The first stars, the population 3 stars that formed from the primordial hydrogen and helium of the Big Bang before any stellar nucleosynthesis had occurred, were fundamentally different objects from stars like UY Scuti. They were likely far more massive, because the lack of heavy elements meant that their molecular clouds could not cool as efficiently, preventing the cloud from fragmenting into the smaller pieces that form lower mass stars. They burned hotter, evolved faster, and produced the first heavy elements from a universe that had contained only hydrogen, helium, and trace amounts of lithium. Those first-generation stars are all long dead. The most massive of them lived for perhaps 1 million years before exploding in supernovae that seeded the surrounding gas with the first heavy elements. Their descendants, the second-generation population 2 stars, formed from gas slightly enriched by those first supernovae, are still present in the galaxy, identifiable by their very low metal content, some of them in globular clusters that formed in the early universe and have survived to the present day. Their compositions carry the chemical signature of the earliest stellar nucleosynthesis, the specific mix of elements produced by the very first supernovae, before subsequent generations of stellar evolution further complexified the mixture. UY Scuti, by contrast, is a population 1 star, a star formed from gas that has been processed by many generations of stellar evolution, enriched with the accumulated output of billions of years of nucleosynthesis in billions of stars. Its composition reflects the full history of chemical evolution in its neighbourhood of the galaxy. Every generation of massive stars that formed, burned, and exploded in that region before it formed has contributed to its initial composition. In this sense, UY Scuti is not just a large star. It is a chemical record, its composition encoding the history of stellar evolution in its region of the galaxy, in the same way that a geological core sample encodes the history of environmental change in the layers of rock and ice that accumulated over time. A star's composition is set at birth from the molecular cloud material available at the time and place of its formation. Reading that composition, through spectroscopy, through isotopic analysis where possible, provides a window into the chemical state of the galaxy at the moment and location of the star's formation. The spectroscopic analysis of UY Scuti's atmosphere is therefore doing 2 things simultaneously. It is measuring the current state of the outer atmosphere, the temperature, velocity field, chemical abundances as modified by the star's own evolutionary processes and mass loss. And it is constraining the initial composition of the star, the chemical fingerprint of the molecular cloud that formed it, the record of all prior stellar nucleosynthesis that contributed to that cloud's composition. These 2 things are entangled. Separating them requires careful modelling of how the star's own evolution has modified the initial composition, but they are both encoded in the spectroscopic data. Future observations with the next generation of extremely large telescopes, the 30-metre telescope, the Extremely Large Telescope, the Giant Magellan Telescope, all currently under construction or in advanced development, will provide spectroscopic measurements of UY Scuti and similar stars at levels of detail not currently achievable. The light collecting area of these instruments, combined with their angular resolution and with modern spectrographic technology, will allow measurements of molecular abundances, isotopic ratios, and velocity fields in the circumstellar envelope at precisions that will transform our understanding of the mass loss mechanism and the chemical enrichment of the interstellar medium by evolved massive stars. Simultaneously, space-based astrometric missions, successors to the Gaia mission, currently mapping the positions and motions of approximately 1 billion stars in the Milky Way with unprecedented precision, will improve the distance measurements for stars like UY Scuti, reducing the uncertainty that currently dominates the uncertainty in the radius estimate. Better distances mean better radius estimates, better luminosity estimates, and better characterization of the stellar population in the inner galaxy. The picture we have of UY Scuti today is, from the perspective of the scientists who will work with the data from these future facilities, a rough sketch, accurate in its broad outlines, but lacking the detail that will make the fine structure of the stellar atmosphere, the three-dimensional geometry of the circumstellar envelope, and the interior structure of the star fully accessible. That progression, from rough sketch to detailed portrait, is the standard trajectory of astronomical knowledge when better instruments become available. Every object that has been studied with progressively improving technology has revealed structure and complexity that was not visible in earlier observations. The solar surface went from a uniform bright disk to a resolved granulation pattern to detailed measurements of individual sunspot structures as telescope technology improved. Stellar atmospheres went from simple spectral classifications to detailed chemical abundances to three-dimensional velocity field mapping. Galaxies went from fuzzy blobs to resolved stellar populations to detailed chemical and kinematic maps of individual regions. UY Scuti will follow the same trajectory. The star visible in current observations, a pulsating, mass-losing red hypergiant with a complex circumstellar envelope, will reveal additional structure and complexity as measurement capabilities improve. Some of that structure will confirm current models. Some will require revision. Some will be entirely unexpected. The unexpected is the most valuable part. Every astronomical object that has been studied in sufficient detail has produced surprises, phenomena not predicted by existing theory, requiring new physics or new modelling approaches to explain. Jupiter's geometric polar cyclones, the asymmetric shape of the heliosphere, the fuzzy core structure revealed by Juno's gravity measurements, the specific composition of the interstellar medium measured by Voyager. Each of these was in the data all along, waiting for instruments sensitive enough to detect it and theories developed enough to recognize what it meant. UY Scuti contains its own surprises, physical phenomena operating in its interior and atmosphere and circumstellar envelope that current instruments and current theory are not yet equipped to recognize. The specific nature of those surprises cannot be predicted. If they could be predicted, they would not be surprises. But the pattern of scientific history says with confidence that they are there, waiting for the right instruments and the right theoretical framework to reveal themselves. This is the condition of science at any frontier, surrounded by what is known, facing a boundary beyond which the known gives way to the unknown, with the specific character of the unknown accessible only by crossing the boundary. The boundary for UY Scuti studies is defined by current instrument sensitivity, current distance measurement precision, and current theoretical models. Each improvement in any of these pushes the boundary outward, revealing more of what is there. What is there, what UY Scuti actually is in its full physical complexity, not the simplified model that current understanding provides, but the actual star with all its structure and dynamics and history, is more detailed, more complex, and more interesting than the current picture. It always is. The universe is always more interesting than our current understanding of it. That is not a statement of defeat. It is a statement of the specific kind of optimism that science is built on. Not the optimism that says we will eventually know everything, but the optimism that says there is always more to know, and that the knowing is worth the effort, and that each generation of scientists inherits a richer understanding than the previous one, and leaves a richer one for the next. UY Scuti has been there for tens of millions of years. It will be there, or its supernova remnant will be there, or its black hole will be drifting through the galaxy, for billions of years after the last human being who currently knows about it is gone. The specific moment in which we are studying it, measuring it, building models of it, debating its radius and its evolutionary state and its eventual fate, this moment is vanishingly brief in the context of its existence. But in this vanishingly brief moment, for the first time in the tens of millions of years since the star formed, something in its vicinity is asking questions.